In this video, I'll give a very quick overview of my paper, Treatment Effect Risk, Bounds, and Inference. So first, let me motivate it with a hypothetical. Suppose you're running some online platform or some app, and you are proposing a change to the system. Maybe you're changing your machine learning pipeline, maybe to be more cost and energy efficient, but that's going to have some changes on the recommendation algorithm that's running your system, and therefore it's going to have an effect on your users. So you run an A/B test to make sure that everything's okay, and maybe see what the effect is in terms of, say, metrics like engagement or retention. And you see that actually the effect on engagement appears to be positive, slightly positive. And the effect of retention is a little hard to see. It's a hard signal, but overall looks like a neutral/positive change. So you say, okay, looks good. Maybe we should deploy it. And they say, okay, wait, let me dig a little bit deeper first, then try to understand maybe what does the effect heterogeneity look like by stratifying by, say, country. So look at the ATE for users in the US, in the UK, et cetera. And some are more positive, some are more neutral. There's a lot of countries overall, but then, oh no, what is this? Denmark looks like it's a negative ATE. But then you think, okay, but how negative is it? Of course, I'm testing a lot of things, so who knows, right? This could just be by chance, and maybe Denmark just consists of a really small proportion of my users, and there's only so much I can do. So you say, I don't know what to do with this. And you could even say, maybe, why am I just stratifying by country? I have so much other data. I could stratify by country and device. I could even go further, stratify by country, device, OS version, app version, et cetera, et cetera, et cetera, past user behavior. I could keep stratifying, right? And then what I will eventually find is I will eventually find some negative effects. I will even find these negative effects, even if I don't really, even if I do something that's valid from the point of view of multiple testing. I could do an omnibus test, like an ANOVA, for some group having a group treatment effect that is different from the population treatment effect. Right, so you could do that, but then still is the question, do we really want to detect any tiny variation in any one tiny group? Because of course it will exist for a rich enough stratification. We don't even have to test that, we know that. At the same time, you might be worried not just about too many groups, but not even not enough groups, because you only have the data that you have. You can only stratify by the variables you have. What about other variables you don't observe, like sensitive attributes like race, gender, income? We can't stratify by them because we don't observe them. And maybe we don't even want to observe them for operational reasons, for privacy reasons, for reputational reasons. So what do we do? Well, in this paper, I propose treatment effect risk as sort of an answer to both of these questions. And what is treatment effect? It's simply equal to what is the smallest within group average treatment effect among all groups that comprise 10% of the population, or 20 or 30 or whatever, right? So it's actually asking the question, what is the average effect on the 10% worst affected, right? The ATE on the population could be positive, could be neutral, but there's still a risk that there is some subpopulation that is experiencing negative change to their experience because of this treatment. So it can answer questions like, what is the group ATE on the 10% worst affected group? Or from the hypothesis testing point of view, once we do inferences, we can ask questions like, does there exist a percent size subpopulation that has a bad effect, where bad could be negative or bad could be significantly less than the ATE? The thing is that this treatment effect risk quantity that I've defined is actually not identifiable from data, whether it's experimental or observational. So in the paper, I do two things. First, I give bounds on this. So for example, an upper bound on the group AT on the 10% worst affected group would be to look at the group AT on the 10% worst affected group that's defined by X values, right? Because that's just restricting the type of groups we can make. And we show that this bound is tight. I also give lower bounds by thinking about what is the unexplained residual heterogeneity, and these bounds are also tight. And then we ask, well, how do we actually conduct inference on these bounds? These bounds just capture the epistemic uncertainty, but then there's also sampling uncertainty, right? How do we assess these bounds from finite data, not just having infinite experimental data, say? So that's a question of estimation and inference. And here I develop a exceedingly robust methodology that is very robust, even if we learn these functions such as the conditional average treatment effect by X, even if we learn such functions using flexible machine learning, or even if we completely misestimated, we're still going to have guarantees that we're going to be consistent, or at least still get a valid upper bound. So that means that whatever we get out of this inference methodology, we can really trust that it's an actual bound on the treatment effect risk. So in particular, if we see that it's negative, that is going to be a clear indication of disparity.